the last thing I want to look at in this particular section, where we've been looking at curve sketching and inequations and what have you, is this idea of asymptotes. I mean, we've talked about them, they have them in the hyperbola, but lots of other shapes have asymptotes as well. And what you'll notice is curves will always bend towards the asymptote. So you get this curvature going towards it. And as x gets bigger and bigger and bigger, it'll get closer and closer and closer to the asymptote. Curves will never cut a vertical asymptote, because a vertical asymptote is telling you an exclusion in the domain. So it can never exist there. But one of the most common mistakes is this one. Curves approach horizontal and oblique asymptotes. You know what I mean by oblique? Right? So lines at an angle. They approach them out at infinity. So they are allowed to cross them at somewhere which is not close to infinity. Now when you think about it, not close to infinity is every number. Okay, I know that sounds weird, but you can think of the biggest possible number you can think of. If it's actually a number, then it's not close to infinity, because you can still go bigger. Right? Now, how do we tell? We usually have this sort of graph where there's a polynomial sitting on top of another polynomial. And as I've been mentioning, the first thing I would do is do a polynomial division and rewrite it. So I'd get my quotient plus my remainder over my divisor. And when it's in this form, it tells me a lot. See, the bottom of the fraction tells me about the domain. So I know, okay, I solve the bottom of the fraction equals 0. And that tells me where the vertical asymptotes are. It turns out the quotient will be the horizontal or the oblique asymptote. And so that's how we know that one. The final piece of the puzzle is the remainder. And if it's possible to solve the remainder equals 0, then that will tell you where it cuts the horizontal or the oblique asymptote. And that's why we've been saying when there is a constant on the top of the fraction, that fraction can't equal 0, because it's impossible for that fraction to equal 0. So you can't have, with our basic hyperbola, 1 on x. I'd go look at the top of the fraction, I say, when can 1 equal 0? Well, it doesn't, so that one never cuts the horizontal asymptote. But people make the mistake in thinking that curves will never cut any horizontal or oblique, and it is possible. But that's how you tell. You look at the remainder, and if the remainder can equal 0, then that's where it will cut. So let's look at some functions here. X plus 3 times x minus 2 over x minus 1, x plus 1. So I've done the hard work there. I've factorised it already. If I do my polynomial division, what I'm really got, the bottom of the fraction is x squared minus 1. Top of the fraction is x squared plus x minus 6. Remember, when you do polynomial divisions, you're really just looking at the leading term. So x squared into x squared goes once, leaves me with a remainder of x minus 5. And that's where I stop with this one, because I can't divide x by x squared. So means I can rewrite this as 1 plus the remainder over the divisor. And looking at that, combining the two together, I can now get a great picture. So I know, looking at the top one, I know where the x-intercepts are, because that's when y equals 0. If I have a fraction equaling 0, it's the top of the fraction that must equal 0. So I know my x-intercepts are at minus 3 and positive 2. So I'll plot those. The y-intercept, again, that's always easy to find. Just sub in x equals 0, I get 6. So I know I'm at 6. Vertical asymptotes. Bottom of the fraction can't equal 0. So I know there are vertical asymptotes at both plus and minus 1. Dot those in. Horizontal asymptote at 1 in this case. Draw that in. Will it cut the horizontal asymptote? And the answer is yes, it will. Because it is possible for this remainder to equal 0. It will equal 0 at x equals 5. So therefore, over at x equals 5, it will cut the asymptote. So all right, let's draw my curve in. I've got to bend towards the asymptote. I go through this x-intercept, bend towards the other asymptote. So I've got that hyperbolic looking thing. Here I go through 6. I can't cut the horizontal asymptote in between. We've determined there's only one place that it does it. It's over there at 5. So therefore, I must be going like a U shape. So I must be bending towards the asymptotes going up. Now, here's the interesting part. The temptation would have been just to draw another hyperbolic curve like this one. But this cuts at 5. So it actually cuts through. Yeah, it was really hard to draw on PowerPoint. I'll do it over here to give you a bit of an idea. What it's trying to do, so it came through at 2, it came through at 5, but it's got to come back and bend towards the asymptote. So at some point, it must turn and inflect and go towards the asymptote. So that's sort of bumpy bit you can see there. That's where I'm trying to get it to turn and come back down. Okay? So most people would probably miss that, would forget about that remainder and just draw a hyperbolic arc in there. But that's not what this particular function does. Let's try this one. Oh, x minus 2, x minus 1, x plus 1 over x plus 2, x minus 3. If I do my polynomial division, x cubed divided by x squared is x. Multiply out, subtract. I can keep going. X squared into minus x squared is minus 1. And that's where I'll stop. My remainder is 4x minus 4. So I can rewrite this one as x minus 1 plus 4x minus 4 on x plus 2, x minus 3. Let's get all our information. X-intercepts, solving y equals 0. So I've got 2, 1, minus 1. Plot them in. Y-intercept, sub in x equals 0, and I will get minus 1/3. Plot that one in. I have vertical asymptotes at -2 and +3. Plot those in. I have an oblique asymptote at y equals x minus 1. So we will draw that in. Now you should know the answer to this question anyway, because looking at the information we've already drawn, will this curve cut the oblique asymptote? Well, the answer has to be yes, because we've already decided that there is an x-intercept at 1. But to confirm that, top of the fraction, 4x minus 4 equals 0. Yeah, that's possible. Add x equals 1. So it confirms the information I already know. What is this one going to look like? Okay, start at the left-hand side. I do not have any x-intercepts on the left-hand side of this asymptote. Therefore, I must be stuck in this little triangle down here. Bend towards the asymptote. Whoop. There we go. So that's that little bit. I wonder if I did the right-hand side before I did the middle. Same thing's going to happen on the right-hand side, because on the right-hand side of this vertical asymptote, there's no x-intercept. So again, I must be stuck in that little triangle up there. The bit in the middle, a little bit more interesting, isn't it? I've got to bend towards the asymptote and keep going. Okay, here's an x-intercept at minus 1. I must be coming down to that x-intercept, because if I was coming up from the asymptote, I would cut the oblique one. But we know the only place it cuts is over here at 1. So it can't come from below, it must come from above. So it'll come from above, it's got to go through minus 1/3 on the y-axis, it will then cut at 1, at some point it's going to have to turn to go through this x-intercept, and then go off to our asymptote. Whee! There we go. So that one I'll do something like that, and let's just complete it. Whoop! There's the bit stuck in the little triangle at the top there. So you get some very interesting looking graphs. And from not a lot of working, we can get a lot of information. All I've done really is that polynomial division, and I can gather a lot of information about asymptotes and what this curve's going to look like. All right. 3G.